Hi there, this is a belated introduction to a video I made a few months ago. It was a lot colder. It was kind of early February, I think. It's now just coming on towards May, so much better weather. The video was basically put together to work out the launch velocity of a basketball using projectile motion equations. So what I basically did was I launched a basketball from position over here and hit the backboard, and the ball went in. Strangely, first time, which is kind of unusual. Okay, so anyway, I hope you enjoy the video. Okay, so having slowed the frame rate down, it's enabled me to track the motion of the ball across the sky in its arc as it moves in a parabola toward the backboard and strikes the backboard. Now what I can then do is put all the frames that I've recorded, and you can probably see there's a nice smooth arc or parabolic path expected by a projectile. I have then reversed the image. This is because I can then actually work in a standard Cartesian form, so I can place a set of XY coordinates, and I have my 0, 0 point on the bottom left, my origin, and you can see that now I've got something to work with on a coordinate system as it tracks the ball across the sky. So initially I'm going to consider the vertical displacement from the time when I launch the ball to when the ball strikes the backboard. So initially we have S, I'm going to call that SI, S initial. Vertically is about 1.6 meters from our scale, and then our final displacement SF is going to be approximately 2.6 meters. So that will make a total displacement from its start position vertically to its end position of 1 meter. I have also created a horizontal displacement. This is referred to often as the range. I'm going to call that X. And from our start point, we're talking roughly 0.4 meters, and our end point roughly is 5.6 meters. So if you subtract the two, we end up with a total range of approximately 5.2 meters. So we can work with these values and some Suvat equations, and we can actually work out the time at which it travels from our launch point to the point at which it hits the backboard, and we can do some further maths and ultimately work out the velocity and hopefully the angle of the launch of the ball from the beginning of the frame. As you can see, I've now drawn a tangent to the parabola at the starting point, which is going to be the angle of the initial velocity, which we're going to call u. Okay. So we've drawn the initial velocity u in, and we are now going to break it down into its two components. We have a vertical component and we have a horizontal component. Our horizontal component we can write as, we'll call this angle theta, which we are yet to determine, and our horizontal component therefore is going to be equal to u cos theta, and our vertical component is going to be u sine theta. So these are going to be used as our initial velocities horizontally and vertically respectively. Now we need to determine what theta is. What I can do is I can drag my conveniently placed protractor and get a rough estimate from our protractor reading on the inside blue, which is approximately equal to 40 degrees. So if I just record that, theta is approximately equal to 40 degrees. So I now have some more information which is going to allow me to start the calculations I need to work out my initial velocity, which is going to be u. Okay? Okay, so we've got all the information we need. So we're now going to do some maths. So initially we're going to start off with our horizontal motion. So we know horizontally we have a horizontal displacement of 5.2 meters. And we also know we have a horizontal velocity of u times cos of 40, and we know if we multiply that, because it's constant, by the time you'll get our horizontal displacement 5.2. So I'm going to rewrite that as ut cos 40 equals 5.2. And that I'm going to label as equation 1. And we have two unknowns. We don't know the time. We also don't know the value of u, which is what we're looking for, the launch velocity. What we can do is we can then consider our vertical motion. So this is vertical motion which is acted upon by gravity, and we're going to use the displacement relation s equals ut plus a half at squared. Once again, we've got flight time t, we've got the acceleration a, which is actually gravity acceleration, and we've got our unknown t and our unknown u. In fact, this u here is our vertical initial velocity, which is actually u sine 40. So that is our vertical initial velocity. So we can rewrite that. We know that s was equal to 1. That's our vertical displacement difference. And we can plug some values in, and we end up with 1 equals u sine 40 times t, so we're going to call that ut sine 40, plus a half. Now, a is actually equal to g, which is equal to negative 9.8, we're round, so that's minus half of 9.8 is 4.9 t squared. So we can rewrite that to become ut sine 40 equals 1 plus 4.9 t squared. And that's going to be our second equation. So we now have two equations. The beauty of this, I'm going to write one above the other. We've got ut cos 40 equals 5.2, and we've got ut sine 40 equals 1 plus 4.9 t squared. We can divide our second equation by our first equation, and we end up with sine 40 over cos 40, or rather write the whole thing, ut sine 40 over ut cos 40. You'll notice that the ut's will cancel, and I end up with 1 plus 4.9 t squared all over 5.2. Now, you should know that sine 40 divided by cos 40 is equivalent to tan 40. Okay, I'm going to multiply both sides by 5.2, and that becomes equal to 1 plus 4.9 t squared. So I'm going to rearrange to get t squared on its own. So t squared is equal to 5.2 tan 40 minus 1, and if I divide all that by 4.9, that will give me t squared. If I plug my values in, I get t as approximately equal to 0.83 seconds. So we're nearly home and dry now. We've just established that t was approximately 0.83 seconds. And I'm going to use my first equation, which was our horizontal motion, where ut cos 40 was equal to 5.2, our horizontal displacement. So if we plug our value of t into that, I can now say that u is equal to 5.2 over t cos 40, and we know that t is equal to 0.83, so u is equal to 5.2 over 0.83 cos 40. Plug in those values in, we end up with an initial launch velocity of approximately 8.2 meters per second. And we are done.